University, and the field speak Nematic cells with Quasicrystalline white layers.
Thank you. And thank you for the invitation to speak here. Do I need to do anything? No. Okay. So let's see. I appended something to my title just to kind of give you a sense of what I'm aiming for here in a tutorial way. So, really the goal here, and I hope you'll see, is that it really comes down to thinking about the energetics and geometry of disclination lines. So I know you've had some, at least one tutorial lecture on topological defects from Randy Kamian, and you've also heard from Lech Longa about disordering in liquid crystals, how to think about that. You've also heard about surface alignment, patterning surface alignment from Professor Yokoyama, so I'll build off of some of that. And so, as I say, my goal here, and especially with using the clicker questions, is just to solidify your thinking in a very straightforward way about the energetics and geometry of disclination lines. And so just to say a little bit about my collaborators, so I'm a theorist, and so I'm the actual, my work that I'll be describing will be the result of simulations and some theoretical analysis that I did in collaboration with several of my students, both undergraduate and graduate. But the real motivation for the system I'm going to describe comes from some very beautiful ideas due to Greg Crawford, who used to be at Brown, but has since gone on to become Dean of Science at Notre Dame, and so he's unfortunately less involved with these things. But he was the one that really had the idea of fabricating these systems that I'll describe to you, and that motivated then the theory. So basically, what we're looking at is Greg's idea of using, somebody's name got whited out there, it's not even mine, using multi-beam photolithography on linear photopolymerizable polymers. So on Tuesday, you were hearing about how you can use light to pattern surfaces in a nematic cell. So there's a nematic cell, sandwiched between glass, and then you have polymer coatings on the glass substrates. So rather than rubbing, we're going to use this idea of orienting the liquid crystals by light and polymers. And what'll be, I think, an extension beyond what you heard on Tuesday is to use several beams of light, coherent beams, but several beams, and that way pattern something with a two-dimensional modulation. So that's kind of the game plan here. So now, I've teased you in the title with quasicrystals, so I hope you're eager to hear about quasicrystals, but whenever you study, if you've learned anything about quasicrystals, to understand quasicrystals, you first have to begin with ordinary crystals. Otherwise, you really don't get a sense of what's different, and also quasicrystals are more complicated than ordinary crystals, so you really always have to begin on the crystal side of things and then move on to quasicrystals. Especially true in this problem. You'll see that when I talk about crystalline patterns, the analysis in the end will be pretty straightforward. When we get to quasicrystalline, it just becomes more complicated. And without the simple insight of the crystalline patterns, it would just be maybe not hopeless to understand the quasicrystals, but it would just wouldn't be as clear, I think, and as straightforward. So what I'm going to do then is spend the first portion of this talk not saying a word yet about quasicrystals, talk about patterning these polymer layers with beams of light that will give me a crystalline pattern, understand what that means in terms of the liquid crystal physics of the nematic sandwiched in between, and then with that insight, go on to the more complicated situation of quasicrystals. Okay, so here's an example of how you could use 4 coherent laser beams to pattern these surfaces and end up, as you'll see, with a crystalline symmetry. So just to orient you to all the geometry here, here's the cell that I showed you before. The z-axis will be along the thickness of the cell, so running from one polymer layer up to the other. And then the way this figure is drawn, imagine the 4 coherent laser beams are actually coming from below. Just happens to be the way this figure was drawn, could have been from above as well. So here are the 4 beams coming in. They are assumed to be polarized as indicated in the XY plane. K is, the wave vector. As you'll see, and I think you can tell by looking at the geometry, what will be what will be relevant to us is the projection of K into the xy plane. So that's what I'll denote as KXY. And so all I'm doing is looking at the superposition of these 4 coherent laser beams in this geometry. And here are the vectors I need to describe the KXY projections, and here are the vectors associated with the polarization that you're seeing in the figure. So very simple geometry. A few things to note about the obvious relation among these vectors. Obvious, if you again look at the picture. And what that means is when I superpose these 4, I really end up just needing 2 of the vectors because of this imaging that you see down here. And the other thing to note is that given the geometry that we've set up here, what I end up with is a net pattern which, while there is time variation in front, it's going to give me a static polarization pattern. And that'll then just give me I could do something more complicated, but this way I have a static anchoring field. So that's the goal here. So that is basically all I'm going to do. And then the question is, fine, here's the math, but what does that really mean when I look at the picture? So here's the picture of what the anchoring field looks like. So all I've done is to take that red term that you saw on the previous slide and just plot it. And what should jump out at you from this is, first of all, I've created this pattern with crystalline symmetry, 4-fold symmetry. So hence, as I said, I was promising you crystalline to start. Then we'll get to quasicrystalline, in that case by superposing, the example I'll show you will be 10 beams. But the other thing that leaps out at you, that hopefully leaps out at you, that's very important, are the point topological defects in this anchoring field. So, the first thing I should emphasize is what I'm going to be showing you or assuming is that I have very strong anchoring of the nematic to these pattern surfaces. And so, when I say, topological defect in an anchoring field, what I'm really thinking of is topological defect in the, nematic right next to it. So, what you see is a pattern here, a regular array of +1 defects at the center, and then what may be a little less obvious, maybe not, but is the -1 defects that occur at these intervening points. And then, just to give you a sense of what kind of numbers we'd be talking about in reality, this spacing could be about 2 microns for light with this wavelength. Theta refers just to that angle, as you saw on the previous slide, the beams are coming in at an oblique angle, and so that's just a measure of that. And so, your KXY is just K sine theta. Okay, so this is, what we're imagining we have. And the other thing I should also emphasize that I may not have already said is that the way these cells are fabricated is they actually create the 2 layers simultaneously in an empty cell. Meaning that what you should be thinking of is a nematic cell where both the top and the bottom look like that, and not only look like that, but they're really just, perfectly matched to each other. That's the geometry. So now, this I think is a good time to bring up a clicker question and to encourage you, like I say, to be thinking about defects and liquid crystal order and things like that. So the question is the following, and then I'll take you through the choices I've indicated, is how will these point defects on these matching alignment layers influence the nematic ordering in the cell? Again, assuming strong anchoring, as I already said. So here are some possibilities that I'll toss out at you. So, we've got these defect points on the anchoring surface. Maybe, there will be defect lines, disclination lines, emerging from these points and just going straight across the cell to the other side. Seems plausible. Maybe another possibility is there just are no defect lines in the cell and you've got uniform nematic order, assuming, you're in the nematic phase. Another possibility is, let's come back to the defect lines going through the cell, but imagine that what they do is they stay close to the alignment layers. They don't traverse the cell. And then, always have to throw in an answer like this, who knows? It's complicated, we need more info. So, in the United States we call this punting, with football in mind. Here, I guess we could call it punting with boats in mind. So, those are your possibilities. And so let me get myself going here. So my mouse comes back. Okay. All right. So you should be off and running. What's a typical time? Sorry? 1 minute. Okay. Everybody good? Not quite a minute. 45. All right, let's stop. Okay, and then let me. Okay, so here is what you guys said. And let me just remind you what you're saying. So, the majority of you, or at least half, it's still the majority, half say, yes, there will be defect lines, and they're just going to go across the cell. Let's see, 2 of you said no defect lines, and then a quarter of you said there will be defect lines near the alignment layers, but not in the interior of the cell. And then, there was no E. Really, that's like, don't bother. Okay, 1 person said don't bother. And then a smaller percentage of you said the punting answer. So, in fact, as we'll see, the answer really is the punting answer.
Not E?
Not. Well, E counts as punting. We'll put in the E with the D. So, those of you that said A, as you'll see, that can occur. And those of you that said C, yes, you weren't thinking of possibilities that just didn't, that couldn't occur physically. But given the information I gave you, I didn't really, give you enough information yet. That's going to be the point here. You really could not answer anything other than D. And just, to quickly, so, you're going to see how A and C kind of arise. So if you were thinking along those lines, I think I will validate your thinking, I hope, at some point, but it'll also get you to think that life is a little more complicated than either A or C. B, just to go over quickly, I don't know if people, how seriously you meant those, but, the thing to keep in mind is that if you're starting, with defects on the surface and you're assuming strong anchoring, just energetically, you can't suddenly, have a defect field like that disappear. It'd be a huge energy cost and mismatch. So that's why, at the very least, we have to have defect lines emerging from these points. What they do is, really the whole story. Okay, so how could you answer the story, answer this question? So one way to do it, I'm going to be showing you, it's going to be over here. So let's one way to do this is to do Monte Carlo simulations. And I know that Mike Allen gave you a tutorial on simulations, but one of the models that he didn't get a chance to tell you about, which is worth noting because it's still an important model, even though it's one of the oldest, or the oldest model for simulating liquid crystals, is a lattice model called the Lee-Wall-Lasher model, which is actually now 40 years old. And it was invented, as I said, as a simple model 40 years ago. Given what you could do with computers then, this was the best you could do. So let me just say a little bit about it. It's a lattice model, meaning you have to only use it in problems where you're not interested in the fluidity of the liquid crystal. It will not tell you anything about smectic liquid crystals. But if you're interested in orientational order in a nematic, if you're interested in the nematic to isotropic transition, it's actually still a very valuable model, even though the fluidity is just absent. And so it's a very simple model. What you do, like I say, is you set up a lattice. There's a picture off in the left lower corner from a review article due to Mark Wilson. And at every site on your cubic lattice, you put a vector u. And what u represents is the average orientation of a cluster of molecules at that point. Remember, individual molecules don't sit on a lattice, it's a liquid. So really what you're saying is, I've got this liquid, and if I look in some small region, I see a bunch of molecules, and they've got some average orientation, that's what I'm calling u. And then I want to know, overall, what's the system doing? And then what I do is write down a simple model. Let's see, in case you're not familiar with this kind of ferromagnetic notation, this just means sum over nearest neighbors. And what you're doing is, remember, in nematics, you don't have a vector order parameter, you really have a tensor order parameter. In other words, it doesn't, if I let u go to minus u, the energy had better not change. And so that's why instead of just having u alpha dot u beta, saying, oh, the u's want to align with each other like they would in a Heisenberg ferromagnet, I square it so that I get rid of, I account for this u goes to minus u symmetry. And then, the reason for the 3/2 minus a half is maybe Lek spoke about the Legendre polynomial that you use to describe nematic order. So, you don't absolutely, need that there. You could, minus a half is a constant in the energy. The 3/2 you could suck into this parameter J that describes, the energy of the alignment, but, it's conventional to write it this way. So it's just a phenomenological model that says, look, the essence of a nematic liquid crystal is the molecules want to align. That's the whole story. And so, this is what, people have used for many different nematic problems, and it's perfectly good for our problem. And so what we're going to do is, take a box like you see here on the left, and given that we have, the top and the bottom with the anchoring field, that's what we'll put in top and bottom, those fixed boundary conditions, the pattern layers. And then on the remaining 4 sides, we'll do the standard periodic boundary conditions that you do in a simulation. Okay, so that's the whole story. So now, what's the result of all of this? So let me show you, I kind of gave you a hint earlier with the clicker question that the answer to the question I posed was, not so simple. I mean, you had right ideas there, but there's a little more going on. And what's going on is really a question of the thickness of the cell, how far apart those pattern layers are. So here's an example of what I'll call a thick cell, meaning that in the units of my cubic lattice, so 1 just means, the spacing between 2 of these u vectors in the Liebowald-Lasher model. For a cell of thickness 40, but compared to A of 20, so A is, like I used earlier, the spacing between the point defects in the alignment layers. I'll call that a thick cell, thickness greater than A. And what you're seeing is that what happens is, yes, there are disclination lines, so you were right to think that, but in fact, in this case, it was, what I think maybe half of you, I think this was like a quarter, the 25% said, well, yeah, there are disclination lines, but they're not threading through the cell. In fact, what they are doing is coming out of these point defects on the alignment layers. So remember, we have a +1 and a -1, but it may not be so obvious from the way this visualization is drawn, but those lines are coming out, and they're just kind of going like a half a lattice spacing underneath the alignment layer, and then joining these points on the same pattern surface. Okay? And the other thing that happens that's worth noting, given your earlier lectures on topological defects and disclination lines, is remember these dots here are plus and -1 integer defects. Yet what we see happening is, rather than creating +1 lines and -1 lines, those things actually immediately bifurcate into 2 half-integer lines. And the reason for that is, at least in this Liebowald-Lasher model, and I think even realistic liquid crystals, it's just lower energy to have a pair of half-integer lines rather than a single integer one. So, they will just come out and then hop over to the nearest point. Let me ask you a quick question without getting into a whole clicker thing. Are you disturbed at all by the fact that here is this, let's go to a black dot, a +1 line. And I'm telling you, okay, great, 2 half-integer plus half lines come out of there. One goes this way, the other goes that way. And then they terminate on -1. the opposite sign. And then, there's more, you might say, remember this continues. There'll be another squiggly line coming in this way. So there's a total of an absolute value of 1 integer charge coming in. But are you disturbed at all by the fact that I have two plus a halves, and they're coming together to a -1? Does that sign difference bother you or not? I'm not sure what you heard from Randy last week. What do you know about plus a half and minus a half disclination lines? Anybody? Okay, they're topologically identical. I don't know if he covered that. But they're actually, whether it's plus a half or minus a half, you can continuously deform one into the other. So there's no issue here of saying, oh, how do I join a +1 and a -1 with these half integer lines? I happen to call them plus a half. They could also be minus a half. I'm not even sure we looked that carefully in the simulation. Okay, so no big deal. So now, before I turn to the next clicker question, let me just get you to pay attention to this picture for a second. So what we have are these lines that are basically hugging the surfaces. So if I look in the cell itself, I won't see these disclination lines. They're right near the patterned layers. So a natural question to ask then, here's the next clicker question, is given that geometry of the defect lines for these thick cells hugging the alignment layers, what's the nature of the nematic order then in the cell? And so, simple possibilities. No nematic order, it's disordered. There's nematic order, it's directed along the x or the y direction. Remember, z is perpendicular. Nematic order in the xy plane along the direction of the defect lines. Remember, the defect lines were kind of going diagonally. Or nematic order diagonal but perpendicular to the defect lines. So let me give you a chance to think about that. And the idea here is to think about, let me just give you a quick hint. Think about the geometry of a half integer defect. What it does to the director as you go around it. That's the key idea. Actually, I have one more. There's time. There we go. Sorry. Okay, 2 seconds left if you haven't. All right, so let's shut it down. And then just drag it over so you guys can see it. Okay. So, all right. Wow, almost a near split between C and D. And so basically, right, you're focusing on this idea that somehow the defect lines are picking out a special direction, which is good. I mean, in that sense, both of those C and D answers get that idea, but there's an issue here of what the proper geometry is. So let me show you the result of the simulations, and then we can talk about the simple physics. Okay, simple, at least once you see it. All right. So let me now show you what I showed you before from the results of the simulations was just focusing on the disclination lines. I mean, I should have emphasized, I didn't show you any of those U vectors. I didn't show you any nematic order parameter. I just said, let's focus on disclination lines. Now what I'm going to do is come back and really show you the U vectors. So, what I'm doing here is slicing through the cell. Each one of these is at a particular Z level. And in the upper left corner, what you're seeing are the actual alignment layers. I've also added the disclination lines, which are actually not in the alignment layer itself. As I said, they're slightly below, but just to kind of orient ourselves to what's going on. Okay, so there's what the alignment layers look like. So in that case, the red are actually the anchoring field. Elsewhere, the reds are meant to be the U vectors. What are these Weeble-Lasher directors doing? And so let's go well into the cell. Here's the midplane. And what you see is that's the correct answer. In other words, that the nematic order is along the defect lines. So now let's look at what's going on here. So, the first thing I want you to focus on is in the anchoring field itself. And that is in the anchoring field, if you just follow any of these either of the dashed blue lines, you see that along those disclination lines, their direction, if you look at how it cuts, how it intersects the anchoring field, it's perpendicular. And that means that if I now go on the other side of the defect lines, I in fact have to end up with a director that is rotated by 90 degrees. So let me maybe explain that one more time just so it's clear. So remember, what's happening is I have these defect lines here, but really between the anchoring field and the defect line, there are messages. There are liquid crystals hanging there. And those liquid crystals are anchored to the anchoring field. So while I said, strictly speaking, since I drew the alignment layer, these red arrows represent the anchoring field, they also represent the liquid crystal right up against the anchoring field. So they're pointing in this direction, this diagonal, right, if you just look along the blue line. But what happens in a half-integer disclination line? Half-integer means if you go full circle around a half-integer disclination line, you rotate by 180 degrees. The half means half of 2 pi. But in this case, we're not looking all the way around. We're saying start behind this blue line, start with those liquid crystal guys, and now as you go away from this, this anchoring layer into the cell, what that means is you've gone around just 90 degrees. Okay, so if this is a defect line coming out towards you, and I have a liquid crystal molecule, let's say like that, if this is a half-integer defect, then when I start going around like that, that's where I end up. I rotate by 90 degrees. So that's why I have to end up with, having started with liquid crystal molecules that were perpendicular to the dashed blue lines here, I have to end up on the other side of the disclination line with the director rotated by 90 degrees. And so that's why that's the correct answer. So now let's move along quickly, at least to the rest of the story and the crystalline stuff so we can get to quasicrystals. So now, I've already kind of prepped you to think that thickness matters. And so you can ask, well, what happens if the cell is thinner? Suppose it's only 6 and the defects are still at 20. Here's the answer. Namely, it's what, quite a few of you said in answer to my first question. What happens to these defect lines? They just thread through the cell. They go from one layer to the other. What you're seeing again is this bifurcation. Just, for the same reason I mentioned earlier. It's just cheaper energetically, rather than to have a +1 line go through like that, it's cheaper to actually bifurcate into 2 half-integer ones. And, you can see that kind of easily here with slices. So here again is slicing now through a thin cell, and if you look, at the mid-plane, what you might do, what I did is I circled this area here, where if you look very closely, you'll see that I have 2 half-integer lines, slightly separated from each other. Okay, so just another view. All right, so at this point, let's get to the moral of the story. In other words, the whole point of showing you this was so that when I now get to the more complicated quasicrystals, it is, you have some physical guidance as to what to look for, what to expect, how to analyze it. So here comes kind of the physical moral of the story. If I give you one of these cells, and I tell you, Greg Crawford has patterned the top and the bottom like this, I've got, some incredible arrangement, whether periodic or quasi-periodic. What I hope I've convinced you of is kind of the first thing I should do is look and see if there are any defects in that anchoring field. And in general, in a two-dimensional patterning, interfering these coherent laser beams, there will be. I mean, if you just did a one-dimensional modulation, you don't necessarily have defects. So, focus on the defects. And again, remember, one of the main points I made earlier was if we've got those defects and we have strong anchoring, we've got nematic disclination lines emerging from those defects. Just energetically, that has to be true. Okay? Then, the whole point of the story was to distinguish thick and thin. For thin, it's energetically favorable for the defect lines to just go right through the cell, join the two layers. For thick, it's actually energetically favorable to not join the layers, but just to have the defect lines hug the layers. And remember that, if you have a thick cell, then you can actually have, nematic order in the cell. And so one way to, and then thick versus thin is just, again, a matter of comparing the thickness to the spacing between the point defects. If you really want kind of a one-line summary, what's the whole story here? The whole story is minimize the length of the defect lines. That's really, a way to summarize the thick and thin. And again, that just means, you're trying to pay the least cost of energy. All right, so that's the moral of the story. So now what I'm going to do in the remaining time is turn to the quasicrystals and try to, play out this analysis as much as I can. As you'll see, it gets, it's not quite as straightforward, but I'll show you at least, what we've tried to do. Okay, so now what we want to do is say, let's consider anchoring fields where instead of having the crystalline symmetry that I just showed you before, I now get quasicrystalline symmetry, which means I really don't have translation. I don't have this perfect repeating pattern like we saw in the square lattice earlier. I have quasi-periodic order, but more importantly, I have a rotational symmetry which can't be fourfold like we saw before, and it can't be 1, 2, 3, or 6, because those would, in those cases, I could have a crystalline symmetry. So we're going to have a rotational symmetry with n not equal to either of those 5 values. Okay, so here's one way to do that. I mean, there are multiple ways, to do this. I'm just going to show you, one particular geometry. The geometry is, let's take 10 beams and such that they follow these 5 directions. So remember, the E's before are telling me the, if you look at the E field here, the EI's are telling me the projection of the wave vector of the incoming beams in the plane of the polymer. Okay, so same notation as earlier. And so I have 10 beams, I have these 5, and they're inverted images. The reason I have to set it up like this, kind of 5 and inverted images, is to get this static pattern, is to have the time-independent part just factor out and give me a static anchoring field. That's the reason for setting it up this way. But otherwise, really very similar to what you saw before. And so, the electric field, again, is polarized in these perpendicular directions, perpendicular to the EI. And what this is going to do is give me, as I'll show you some pictures shortly, an alignment layer with tenfold quasicrystalline symmetry. And the electric field actually has 5-fold because it has a direction. But remember, in the anchoring field, we're talking about anchoring to a liquid crystal. There is no direction. It's an axis, so it's actually tenfold symmetry. And whether it's 5-fold, tenfold, the point is there's a theorem from solid-state physics. If you have 5-fold or tenfold symmetry, you can't have ordinary crystalline order. It's just impossible. Okay, so remember the program. The program was, I give you this. The first thing I should ask myself is, where are the defects in this field? And I have to show you a picture, but better to do a little analysis first, since it's a little less obvious than in the crystalline case. So how can we find the defects in the anchoring field, just algebraically, before even looking at a picture? So one nice way to do this that my student Michael Schwartz came up with is consider a vector perpendicular to the E field. And you can then show, if you just go back to the E field out on the previous slide, that you get the following identity. And what's nice about this identity, the reason it's helpful to have, is it says that this E perp, the thing that's perpendicular to E, is perpendicular to curves of constant phi. So phi is just what's inside this gradient. And E, because it's perpendicular to E perp, will be tangent to these curves. So I'm just using the property of a gradient and the fact that gradient of this phi is along E perp. That's what gives me these statements. And you can work out phi, right? I gave you the E field on the previous slide. Here's what you get. And now the defects in the anchoring field will occur at critical points of phi. Let me just give you it algebraically, and then I'll show you a picture. So critical points just means I'm looking at maxima and minima. It's kind of like doing electrostatics. It's like saying, I'm doing electrostatics, and I am looking for, maxima or minima in the potential, and then I say, oh, great, I've got an electric charge there, and the E field is, coming radially outward. That's really all I'm saying in this first bullet. And then, because we're not doing electrostatics really, I can also have saddle points, which will actually be charge -1. And I can, find all of these critical points just by looking at the Hessian. So let me show you a picture just to make it, the algebra stand out a little more. So here's a picture where I'm plotting for you the E field, but I'm also plotting this phi. And the only thing to note that's not obvious from this scale is that it's actually the white areas that are the large values of phi. So remember, what I'm doing is to find the defects in the E field, I am looking for these critical points of phi. I'm looking for maxima and minima. I'm looking for what I've indicated here in white. And so if you pick a white point and start looking, you'll see that it is, where's a good one? You'll see that it's basically got a defect-like structure in the E field. Wherever you look at the white, there's actually a saddle point in the middle here. But let's, you can see these patterns here in the white where I've got defects in the electric field. Okay? But again, it may not be something where you would look at the picture and it would immediately jump out at you the way it did in the crystalline case, but we do have this algebraic algorithm. Here's how to find the defects. Okay, so now I could ask you all the questions I did earlier. I could say, great, got all this mess of defects here. I could have a thick cell, I could have a thin cell. What are the disclination lines going to do? And obviously, thickness will matter, but you may be already getting an idea that things are a little more complicated here because the defects are not in this nice, beautiful grid where I can just easily join them by defect lines and, immediately figure out what's going on. So clearly, I want to do a simulation. So, again, we do a simulation, but there's a bit of a conundrum here, which fortunately people have, gotten themselves beyond. The problem, at least at first glance, is how do I do a simulation on a system that's not periodic? Whenever you do a simulation, just given, even our great computers now are not powerful enough that we can avoid periodic boundary conditions. We've got to do that because our systems are, even on supercomputers, way too small. So how do I deal with a system where there is no periodicity? How am I going to do periodic boundary conditions? So there is a way to do that, and that is to use a periodic approximant to the Penrose tiling. And so there's a paper by Enton, Bowman, and Clayman which does this, actually some others as well. And this is something actually, I was just reading scientific news today. This idea of periodic approximants is actually important in materials physics. People are actually fabricating systems in the lab where they can really, this is not just a trick for simulations, but they can actually make what amounts to periodic approximants to Penrose tiling. So in any case, what you do is you just have to slightly adjust 3 of these vectors. And in effect, what you're doing is, buried inside the quasicrystal, for those of you that know something about Penrose tiling and quasicrystal, is the golden ratio. And so a way you can get a periodic approximate to the Penrose tiling is to replace that irrational number, the golden ratio, by a rational number, in particular successive Fibonacci numbers. And as n goes to infinity, that ratio will approach the golden mean. And once you do that, once you get rid of that irrationality, you actually end up with a periodic structure. And what that periodic structure looks like, here's the unit cell, which I've drawn for a particular, in this case, n equals 3 approximation to the golden mean. So that corresponds to a tau n of 1.67, whereas the golden ratio rounded off is 1.62. So this is going to be our unit cell, this rhombus here. Again, if you know something about Penrose tilings, you know, seeing a rhombus should not surprise you. And so this is the unit cell of our periodic approximant. So given those E vectors, those wiggled E vectors, what I have is a system, an anchoring field, where this rhombus will just repeat itself over and over periodically. But what's happening is that, if, you know, again, not so obvious in here, and I don't have a good comparative picture, is that the E field that I have in here is at least some approximation to the E field that I showed you earlier with its fivefold symmetry. And maybe you'll see it if you look at it, maybe not. Okay, so then what we do is just leave wall lasher. We make a simulation box, which is a right rhombic prism. Okay, so the anchoring layers look like what I showed you in the previous slide, and then they're just, you know, stacked up like that to form a cell of height h. And then, you know, you can write down your rhombic prism lattice, putting your U vectors at sites like this, the alignment layers at 1 and h. We take k, you know, kind of with experimental motivation, you know, roughly in roundish numbers, 500 nanometers for lambda, k is of order a half, and then the size of our unit cell comes from the theory of the Penrose approximants, and what we want is to make that, you know, close to an integer value. Okay, so we're trying to, you know, just index our points in our Leibol-Lasher model with L. Okay, so that's the basic idea. And then, so what happens? Let me talk now about what occurs. So here is an example of a thick cell. So what I've put in bold here, just so it's clear, is that, I mean, you might look at this and say, oh yeah, you know, here are 10-ish disclination lines, you know, going through, but then all this other stuff that I've drawn, that's up on the alignment layer, you know, it's got nothing to do with defect lines. In fact, you know, the picture is so complicated, it's hard to draw it any better. All of these blue lines you see, whether up here or threading through the cell, are all these half-integer disclination lines. And they're just a slew of them, given this geometry. And so what you should be focusing on is this idea that it's a thick cell, and earlier I told you, oh, thick cells don't even want lines going through them. So it's a little, you know, not so simple here. But the other thing that should make some sense to you is that I have a thick cell, and there are lots of disclination lines hugging these alignment layers in a very complicated way, but that's where they are. Now, I won't show you a picture of a thin cell, because not surprisingly, with so many defect lines, you know, you would just see this mess, you know, threading through the cell. There's no point. But now, let me spend just the last, you know, 2 minutes or so giving you some sense of how my collaborator, my student Michael Schwartz, came up with a very nice way to think about how do we characterize thick versus thin. You know, how are the defect points really connecting here? And so the way you can do that is by taking the picture I showed you earlier and actually overlaying the Penrose tiling, which, for those of you that know something about Penrose tilings, they may look a little odd here. I have some hexagons and a decagon in the middle. You can actually subdivide those further into rhombi, but it hasn't been done here. But the thing that Michael noticed was that if you look at what's called a thick rhombus here, so the Penrose tiling will have a thick rhombus like this one, and then there's a thin rhombus, you can see one over here, that what he noticed is that, maybe not with mathematical certainty, but pretty close, the +1 defects tend to occur at the vertices of these thick rhombuses, and the -1s at the center. And, you know, there's another example here that I'll just, you know, bring up for a second if you want to just eyeball it and see if you agree. So then his idea was, if you want to understand thick versus thin, let's look at the fraction of defect lines joining opposite sides of the cell as a function of cell thickness, you know, just like we would have done in the crystalline case. And, you know, when we look at our data for different values of L, you know, the unit cells we've studied, you know, we get data that looks like this for this fraction as a function of thickness. But the way to make sense of, you know, what's setting the scale for the drop-off in this curve is to make use of that picture I showed you a moment ago, this idea of the +1 defects being at the vertices, the -1s at the center, here's a rhombus. So all I need to do is just go to the simple geometry of this Penrose rhombus based on 36-degree angle, and there's the golden mean again that comes into L. And that will give me values for L1 and L2. So remember, there's one defect at the center, and the other defect is going to be at one of the vertices. So the relevant lengths to focus on for thinking about how disclination lines join defects are L1 and L2. So if you add L1 and L2 to these plots, it gives you a sense then of exactly the physics I was telling you earlier in the crystalline case. In other words, let's minimize the length of the disclination lines. And so I have to know, if I start on a patterned layer, how far do I have to go to join up to point defects? And so L1 and L2 will tell me that. So that's the sense of this figure. Okay, so let me, since I'm already up to 44 minutes, let me summarize. So basically, what I hope I've shown you is that, and this is really Greg Crawford's contribution, is that you can pattern these surface anchoring fields with multi-beam lithography, and you can make crystalline, you can make quasicrystalline symmetry, and then given that, you're going to, in general, be producing point defects in the anchoring field, and given that, you're going to have disclination lines that will go through the cell. The key point is, energetically, the disclination lines want to minimize their length, and so the way they will do that is either join the defect points on the same anchoring surface or traverse the cell, and all of that depends, in general on thickness. In the quasicrystalline case, it's not, it depends on thickness, but in a somewhat complicated way. But still, in the end, thickness is the key point that one has to consider. So, that's it.
Questions?
Yes.
So what, if you would look in a section, see in the first case with the square letters.
Yep.
In a section perpendicular to the screen.
Okay.
That contains the defect line.
Yes.
When it starts out, when it goes up,
Yep.
it comes back down again.
Let's see. So you want me to do a select, like this is the z-axis? Is that what you're saying?
Yeah.
Yes.
Let's say we have a very thick cell.
Yep.
Then we have.
Okay, so in other words, like what would you see? Yeah, I probably didn't have a great picture. Yeah, so it's something like, if this is, let's say, a +1 and a -1, the half integer thing is how I'm doing something like that, and then, it always bifurcates.
Right. So.
And then in the middle, once you get in a little bit, you will then get, very strong nematic order along that, line, direction of the, I guess the way I've drawn it here, be like that.
So how far up do they get?
The defect lines?
Yeah.
In the simulations, they are like really hugging, they are, the way the algorithm works in these things, when you find a defect line in a lattice model, the defect line actually lies in the center of the plaquette. So in other words, if this is the unit cell of the Lee-Wall actor model, and here are your U vectors, and, well, I haven't drawn a defect here, but if I did draw, something that corresponded to a defect pattern, the defect, kind of by the definition you give it, is piercing the plaquette like that. So these defect lines are actually just literally a half lattice spacing in.
But they couldn't be like in the next one?
I mean, they could in principle, but I think we were, at least for the simulations we did, we were always finding them really hugging the surface, at least for the parameters we looked at.
So I guess you calculate the ground state structures.
Yes. Yeah.
But I would imagine that there could be also a zoo of metastable
Yes,
states that
yes.
in experimental systems
Yes.
could be realized in addition to the ground
Yes,
state.
definitely, right. We were just focusing on ground state. And, yeah, like I say, the unfortunate part of this is, Greg left ground, so, what might have proceeded as a, a longer-term theory, experiment, collaboration, unfortunately, didn't continue. But, yeah, I agree. There can be, I'm showing you kind of a straightforward framework.
So here you draw the wedge distillation that
This one here?
yeah.
Yeah.
But I can only visualize twist distillation going on in the actual. Is that true, or you actually see?
So let's see, yeah, right, now as I was drawing this, I'm thinking right as I'm showing you the right. So let's see, yeah, so it should be, right, a twist distillation. So let's see, I had, let me see how fast I can do that in my head. Right, so I had a picture, I said, oh, here's a defect line, and behind here, I have, let's say, a molecule like that, and then it's turning to something like that. And so, right, the rotate, yes, yeah. Yeah, so that picture was, right, just off the top of my head. Yes?
I don't know if you recall, so when Greg did these experiments, and I think you had mentioned that you could sort of get a periodicity down to about 2 microns for the arrays. This is earlier in the talk.
Yes, yeah.
Okay, so in real life, anchoring is not infinite. And if he has a 2 micron periodicity, did he end up just getting a liquid crystal on top? Does the director pattern just end up washing out because of elasticity?
So let me see what I brought, like I said, we've never, in the end, or maybe I should just show you that later. I do have one, tentative, optical pattern that he gave us.
So most of these then were things that he's patterned but did not look liquid crystal after being patterned.
Right, so he feeds in the liquid crystal, right, he patterns, and then adds the liquid crystal afterwards.
And there's only one image of that?
I'm sorry?
Oh, we'll talk.
Yeah, we should talk separately. Like I said, yeah, there was nothing that I think he ever published, and so I wasn't, yeah.
Okay.
That's why I didn't even show it here, because it was pretty tentative stuff. But yeah, I can show you that separately.
Any other questions?